Dear students, greetings and warm welcome. We are into week 7, class 1. So, today's classroom discussion topic is dynamic and wear failure of gears. So, lecture learning outcome. After completion of this lecture, you will be able to analyze the dynamic failure of gears and analyze the wear failure of gears. Here, in dynamic tooth load, the loads are due to the following reasons. One is inaccuracies, the dynamic loads are due to the inaccuracies of tooth spacing, irregularities in tooth profiles, and deflection of tooth under load. These are three parameters on which dynamic tooth load depends. Okay, one is inaccuracy, irregularity, deflection. So, what are inaccuracies and what are irregularities? Deflections of teeth. We'll see them. Okay, and we'll discuss them. So before that, a closer approximation to the actual conditions may be made by the use of equation based on extensive series of tests. There are a lot of tests done to derive this equation. Okay, that is WD equal to WT plus WI. That is total dynamic load is equal to steady load due to transmitted torque WT plus incremental load due to dynamic action. So that incremental load WI depends on pitch line velocity, phase width, material of the gear, accuracy of cut, and tangential load. The average condition, the dynamic load is determined using Buckingham equation. I'll show you the Buckingham equation now. So this is a Buckingham equation. WD is equal to WT plus WI. So here in Buckingham equation, incremental load is expressed in this form in terms of pitch line velocity, phase width, small b, and a deformation or dynamic factor called C, capital C. Its units are Newton per mm. So the deformation factor depends on the error between teeth, class of cut, tooth form, material of gears. And here is a table which shows various deformation factor values, which depends on dynamic load of gears. So the table is like this. So pinion and gear, if pinion is cast iron and gear is also cast iron, and if the tooth profile is 14.5 degrees involute tooth, and C values will depends on tooth error in action. E, small e, if it is 0.01, the value will be 55. If it is 0.06, the value will be 330. Like that, various forms, various factors are defined here based on various tests. So this data will be available in data book. So coming to the actual relation of C, it is defined by the following relation: C equal to K into E by 1 by EP. EP is Young's modulus for pinion. EG is Young's modulus for gear. K is a factor depending upon the teeth. It is 0.01, not 0.7 for 14.5 degree full depth involute system. It will be 0.0111 for 20 degree full depth involute system. And it is 0.115 for 20 degree stub system. Like that, there are various parameters defined here. E depends upon pitch line velocity and class of cut, as I said earlier. Okay. The following tables will define the small e for different pitch line velocities and modules. So here is another parameter, static tooth load. Static tooth load, also called as beam strength or endurance strength of teeth, is obtained by Levy's formula by substituting flexural endurance limit or elastic limit sigma E in place of working stress sigma W. So the static tooth load equation is Ws equal to sigma E B into Pc into Y, whereas we can write Pc in terms of pi and module m, pi m. So this is a static tooth load equation Ws. We have seen WD, WT, WI, Ws now, static tooth load. And now wear load. The maximum load that gear teeth can carry without premature wear depends upon radii of curvature of tooth profiles and on elasticity and surface fatigue limits of materials. The maximum or limiting load for satisfactory wear of gear teeth is obtained by using the following Buckingham equation. The maximum load that a gear teeth can carry without premature wear is denoted like this. Okay, WW equal to dP small v q into k, where this one is wear load, dP is diametral pitch or pitch circle diameter, pinion, uh, small b, as we all know, face width. Q is a ratio factor. It is 2 into VR plus by VR plus 1, that is equal to 2 into TG for external gears. It is for internal gears. It is sum for internal gears and subtraction for internal gears. Sum for external gears, where VR is velocity ratio, that is TG by TP. Load stress factor, also known as material combination factor. Okay, this is wear tooth load. So this one is capital K designation. It depends on maximum fatigue limits of compressive stress. K, its relation is given like this, where phi is pressure angle, EP is Young's modulus, EG is Young's modulus for gear. So here is a reflection spot 1. Kindly answer with a prior knowledge of previous slides. Static tooth load should be lesser than, greater than, or equal to the dynamic tooth load. Static tooth load should be always. So your time begins now. 15 seconds of time is being given to answer this. Static tooth load should be greater than the dynamic tooth load. The answer is B. Coming to the numerical problem based on the learned things. Here is a question. A pair of straight spur teeth having 20-degree involute full depth teeth is to transmit 12 kilowatt at a 300 rpm of pinion. The speed ratio is 3:1. The allowable static stress per gear of cast iron and pinion of steel are 60 megapascal, 105 megapascal respectively. Cast iron gear and steel pinion. Assume the following: number of teeth on pinion, face width small b, velocity factor cv, everything is given. So he is asking us to determine module, face width, pitch diameter. Check the gears for wear. Okay. Here is a hint. V equal to, okay, I am giving some hints to solve the problem. WT, CV. So based on this hint, please kindly solve the problem. Form factor for pinion, form factor for gear, tangential tooth load, face width small b, pitch diameter dg equal to modulo tg. And finally, we have to check for the gear for wear. Use these formulas to solve the problem. Here are some hints to solve the problem. Okay. So I'm ending here. So upon completion of this lecture, you will be able to analyze the dynamic and wear failure of gears. Okay. So happy learning. Thank you all. Have a great day.